So that's regarding part 3. I have these things, just remind me and take it before you leave. I got it last week and I forgot. This is the homework part 2 of part homework 2, I guess, which is the anatomy of Google thing. So, okay. Any questions? So the agenda today is complete the discussion of recommendation systems, in particular the collaborative filtering that we started talking about last time, and then actually go into search advertising, which is also, advertisements are also recommendations, right? Because they're recommending stuff to you, and in doing so they get paid by somebody else. Okay. So in fact, advertisements are a kind of sponsored recommendations, whereas normal recommendations are Amazon is recommending it to you so that maybe you'll buy more stuff from them, okay, or just to make you happy. So the interesting thing when you get to search advertising is there are more parties. Here essentially it's the search engine and you, that's it. You know, when you're recommending, it's either the search engine or the company which is doing the recommendation to you, and you yourself, whether you like the recommendation or not. Okay. When you get to advertising, there are 3 parties. There is the user, there is the thing that is doing the recommendations of the advertisements, which is search engine, and then the people who want their advertisements to be placed, which are the advertisers. And so it's a more interesting problem. We'll look at that a little also. Obviously, you all know search advertisement is the reason why most search engine companies are actually alive right now. Most of internet is alive with advertising. So we'll look at that. Okay, so that's basically the agenda. Any questions on collaborative filtering? Okay, so the one thing that I was mentioning at the end of last class was that between content-based filtering and collaborative filtering, content-based filtering is domain sensitive. That means it actually needs to know what it is that it is recommending. And collaborative filtering is domain free because it doesn't know what it is recommending. The only reason it's recommending them to you is because people like you who bought various other things, so that's why they are like you. These are the ones that they also bought. So they bought this other item and maybe you will be interested in it. Okay. In some sense, the items are connected only because of correlation between the users who are buying them. And this is exactly what we did in finding association clusters for the words. When we found that computer is connected to science, it's not really the case that computer is equal to science. It's just that every document which had computer also happened to have science. Okay, so here basically in collaborative filtering, you can think of users as the documents and items as the words. And everything you know about co-occurrence analysis can be done here again. Okay, so I just get to do it again once more. The only minor change is you are aware of the fact, unlike in documents, so basically the big analogy here in collaborative filtering is documents, users, words, items. That's the analogy, right? So you can do associate doc similarity matrix, word similarity matrix, and then from that you can compute which words are more similar to other words. You can also compute which documents are more similar to other documents. This is all stuff we have done. So you can do that here too, which users are more similar to other users in terms of their buying patterns, which items are more similar to other items in the sense that people who buy these items are also buying these other items. Okay. The only interesting thing, so pretty much we will just transfer our insights from here to here and call it collaborative filtering. The only difference really is when you're thinking about documents can have large numbers of words, you know, whereas users typically may not be buying enough items. Okay, and so because of which there may not be enough co-occurrence information that you may be able to derive. If in fact it turns out most users are not buying enough items, they are not good enough consumers, then essentially if they haven't bought or if they have not rated that item, essentially, then that item is not part of the user bag. So if the word is not part of the document, that means the document doesn't like the word. That's clear. If an item is not part of the items that the user has rated, that doesn't mean that the user doesn't like the item. It only means the user hasn't yet bought that item. So that's the distinction. And so we will actually deal with that with a few variations on the association cluster idea. Okay, so let's go to association clusters applied to items and users. So just as you had document term matrix, you can start with an item user matrix. Okay, and then you can do your association clusters and scalar clusters and everything. Okay, so if you think of, you can either think of users as the vectors in the space of items, or think of items as vectors in the space of users. Okay, if you do either, then you can actually do vector similarity between users or vector similarity between items. Okay, in fact, that's pretty much what we will do. The only difference we'll do is we'll actually talk of something called Pearson correlation coefficient, which turns out to be vector similarity on the ratings vector, except they take the ratings vector and center it. So the idea is, if I have rated something between 1 to 10, okay, and my ratings are, so here are my items that I have, I1, I2, etc., I7, and then I rated it 2, this is 4, this is 9, this is 5, let's say. That's the ratings vector. Okay, what is actually more interesting to me is not what the rating that the user gave, but really what's the mean of the user's rating, and what is the difference of each of the items from their average. So because some users are easy to please, they think everything is great, so they give it more like 9 all the time. Okay, some people are really, really hard to please. They'll only give up to 3 in the rating. So if somebody gives a 3, so and who never gives more than 3, then that's like an A+. Like in this class, I mean, if you get like 50% on the exam, it could be an A+, right? So what matters is how far are you from the average. Okay, so you center the vector by essentially taking the mu, which is the average of the ratings, and then essentially taking 2 minus mu, 4 minus mu, 9 minus mu, 5 minus mu. That's your centered ratings vector. Now if you take vector similarity between the centered rating vectors, that actually can be also seen as what is called Pearson correlation coefficient. We'll see that in a minute. Okay, it turns out that the vector similarity between centered rating vectors can be interpreted in terms of variance and covariance over vectors, over ratings. Okay, so people basically think of the distance, the similarity measure they say they're using is the Pearson correlation coefficient, which is just vector similarity on centered vectors, centered rating vectors. Okay, and then you can do that. Once I have a similarity metric, I can compute the similarity between users. I can also compute similarity between items. I mean, I can also do item-item clusters. Okay, so in the beginning, the traditional idea for collaborative filtering is to actually figure out who your neighbors are. That's the picture that I showed you here. Here is a current user, and you figure out who their close soulmates are in terms of how similar they are to this user. And then you want to see how are they rating this particular item C. And then you want to predict this guy's rating for C as a weighted average of his or her most similar neighbor's rating for C. That's the simple idea of collaborative filtering. Okay, actually it's not simple. That's the first idea of collaborative filtering. That's what I will describe. Okay, but there's a much simpler idea where you can ignore who your neighbors are, and you can just compute item-item correlation matrix. And then I don't need to know about the users. If you remember term correlation matrix and you find the association clusters for the terms, then I don't need to know who are the documents, where did I get these numbers from. In fact, it will be I by I matrix. Right? And then, so if this guy has a few of these items, given each of these items, I can see what other items they're close to and then just suggest to them. That's a different way of doing collaborative filtering. That's called item-centered collaborative filtering. Okay? So the first idea, of course, is user-centered collaborative filtering, where you weight all the users with respect to their similarity to the active user, the user that for whom you're trying to do the recommendation. And as I said, you measure similarity essentially as a variance of vector similarity, okay, over rated centered vectors. And then of these users, then you select a subset of these users as saying these are your k nearest neighbors. Okay, and then you want to consider your rating for the missing items. I want to predict as their rating for a particular missing item. That is the item for which the active user doesn't have a rating yet. And so you want to see whether they like it. Okay, so you will predict that item's rating as a weighted sum of the ratings of the individual, of his neighbors. Okay, I'll give you the details. Okay, and then having done this, then you have computed the ratings for all the items that the user doesn't already own. Okay, and then among them see which ones have high enough ratings and say you may be interested in buying these. So I show you. That's what is collaborative. Okay, so the idea of Pearson correlation coefficient essentially is given the ratings vectors. The covariance of the rating vector of, let's say, active user A. So each user is represented in terms of their ratings over the items, right? So in the document's case, each document is represented in terms of the frequency of each of the terms in that document. Similarly here, instead of frequency for the items, you're talking about the ratings for the items. Okay, so Pearson correlation coefficient is nothing but covariance of the two rating vectors RA and RU divided by the variance of the variance of RA, standard deviation of RA and standard deviation of RU. Okay, now what are those? So standard deviation, so again, covariance is you take the vector of RA, and then you center it. The way you center it is you subtract from each of the ratings the average rating of A. Okay, and similarly for U, you subtract average rating of U. Okay, and then you multiply those two and you sum over all the pairs, all the corresponding pairs. Yeah.
It's like vector similarity.
That's what this is basically vector similarity over centered vectors. It's just it's called Pearson correlation coefficient. It comes from a different area, but it's the same idea. It's again a dot product. Okay, so that's covariance, and then the variance. So the standard deviations essentially are basically just a square. So covariance between a vector and itself is the standard, and the square root of that is the standard deviation. Okay, so that's what you're saying here. Okay, and if I do this, then I can compute this measure, the correlation coefficient between A and U, as the covariance of RA RU divided by this. Now notice that you can only compute the covariance over the items that are common between both of them. So the average rating for each user is the average over all of their ratings. But the numbers that actually come here were only for those ones which both of them have rated together. Because if one of them rated and the other didn't rate, then how am I going to get this number at all? Okay, so it's a biased estimate. It's estimating similarity only over the items that both of them have rated. And that is something you want to keep in mind. Okay, in a document, if there is no word, that means the word is not liked. In item vector, if there is no item, if an item has no rating, that doesn't mean that I don't like the item. In fact, I just don't know about that item. Okay, so you are forced to essentially consider only this computation is done only over the vectors that are rated. Only the items that are rated. Yes?
So we are considering how generous or how hard the neighbors are.
No, I mean, the average for each user, you do take their average over all their ratings. So suppose I rated 10 items, you rated 20 items. Together, we only have 3 items in common. So this product is going to be only over 3 items. But the averages are my average over my 10 items and your average over your 20 items. That tells you more about, whether you are an easy to please or hard to please person. Okay? So that's the idea. Okay? And this is just saying that Pearson correlation coefficient is nothing but vector similarity over centered vectors. Okay? Covariance is dot product, and the square root of variance of each vector is nothing but norm of each vector. So you're actually computing exactly the vector similarity, over these centered vectors. Okay. Now, after doing this, you have computed the similarities between the current user and all the users in the database, in the customer database, and you need to pick some K users, top K users that are closest to this user. Okay, and then you'll pick the K users, and then the question, of course, is how do I then compute the rating for the ith item, predicted rating for the ith item for the active user? Presumably, that's because ith item has not yet been rated by this active user. I mean, you can compute what should have been your rating, and then, of course, tell you that you made a mistake in buying this item, you should return it because you're not supposed to like this item. Right? I mean, that also can be done. Okay? But we will not, since I'm only interested in selling stuff, I'm not interested in changing your home, I'm only going to tell you, the items that you haven't yet bought, whether you should buy them. Okay? So, what do I do? How do I do that? Again, in this case too, I will assume that the item that you haven't yet seen, you the active user haven't yet seen, you're likely to give it the average rating. If I don't know anything else, you will give your average rating. If you're an easy to please person, you're likely to give something 7+. Hard to please person, something 0+. Okay? And then the question is, what is the plus? Plus can be, positive or negative too, actually. Right? And so I'm now computing the differential here. And all I'm doing in this case is, the differential is being computed by, I'm taking your K close by neighbors. For each of the neighbors, I'm computing their differential for this item. Okay, so that means the user U has an average rating R dash U, and they have given the specific rating to the ith item RUI. So they gave this much as the differential. This could be positive or negative. They either liked it more than average or less than average among their positions. Okay, and then this user U is, WAU close to you. This is their similarity to you. So you multiply this differential by this similarity. That's your weighted summation of the differentials divided by the similarity measures. Okay? That would give you essentially the average differential that you should add to RA. And you add that and you will get the predicted rate. Yes?
So do you assume that all of your K-closest neighbors have that rated? Or like
Yes, yes. You're only considering the ones which have rated the item. You're only considering the user, as the neighbors which have rated the item. So in fact, if somebody did, then they are not going to take part in this computation. So this business of sparse ratings is a big issue in collaborative filtering. You notice that that was a problem in computing the similarity. It's also a problem in here. In fact, it's actually, the next question that I'm going to ask is, so is this good enough? So this is basically the simple idea of user-centric collaborative filtering. Okay, yes?
What about when a new user has come into the system and logged into the
then that's fine, you just do it. But I don't know that.
But there is no average rating for that particular user, right? And there is no weight to other.
No, that's basically, you're talking about the cold start issue. That means if somebody doesn't have any ratings already, then you can't use collaborative filtering. That's a big problem in general for collaborative filtering. Okay, then I have to make assumptions that maybe you're an average user, so you will have an average rating of all the users, average. Something. Otherwise, I can't say anything. Okay? And so collaborative filtering becomes more useful after people have put certain number of ratings. And also, it's a very interesting point, equivalently, that's related to you. If this is a completely new book, it hasn't yet been bought and rated by anybody. So nobody is going to have a rating. None of your K neighbors are going to have a rating for it. So you know no more than saying, I would just like this book the average way I like books. If I'm a big bibliophile, I probably give something 6 plus. If I hate books, I start with 0 plus or 0 minus, right? So now the problem is, again, that's another cold start problem. That means if it hasn't been, if it's a new item, it hasn't actually been rated, you can't give other people any predictions on that. But content-based filtering doesn't have a problem. Because if you have liked books with these words in the past, then probably you will like this book because this book also has these words in the title. Okay. One slight change improvement, this is kind of a useful thing to do in collaborative filtering, is you shouldn't just care about the similarity, you should care about similarity and the significance. The idea is that you might have, rated, let's say, 20 items. You, the active user, have rated 20 items. Here is the user 1 who has rated 100 items, okay, of which they only have in common with you 2 items. 2 items in common. Another U2 has rated maybe 200 items, okay, and they have in common with you, 17 items. Okay, now it may well be the case that this guy rated these 2 items that you rated along with him, you are like soulmates. And these 2 things, you're soulmates. You agreed completely. Because of which your similarity would be 1. Whereas this has 17 items, so they have a lot more experience, common shared experience with you, of items at least. And they may have rated it, and the question then is, should I care more about, and they may actually be less similar to you. And my favorite example for this, and sometimes I ask about this, is the way, let's say, you might have had a long-suffering spouse. I don't know how many of you have, wives and husbands. And, at the time when you started going out with them, you probably, liked them or something. After a long time, you seem to agree on some things, disagree on some things, okay? And then at some point of time, you started having an affair with somebody else. Not again, against family values, you should follow family values. But if you did have an affair, what's likely to happen is the first few days of the heady affair, you're likely to agree on everything. Right? Now, so there is this person, long-suffering spouse, and there is this new flame, and there is a new movie in town. The spouse says, I hated this movie. And the flame says, I love the movie. The question is, are you likely to like the movie or hate the movie? Okay? That's the question. And obviously you think, the new flame is likely to agree with you on everything, and but your shared experience corresponds to 2 movies that you have seen till now. Okay? And you kind of like both of them, or at least you're too polite to disagree with each other, and you sort of suffered through both of them. Whereas the long-suffering spouse probably has a lot more experiences with you, and you have a better idea as to whether or not that similarity should be moved. Okay? So this is the long-suffering spouse clause, which is a significance is added, and so apart from the similarity that you compute, you multiply it by a significance factor. The significance factor basically would be 1.0 if you have enough experience, common experience together. It doesn't matter that you rated them the same way. If you have a long-suffering spouse who always disagrees with you, that's an extremely useful predictor. So if that person didn't like the movie, then you would love the movie. The problem is not that, it's a question of just a prediction. We're not trying to take them to the movie. You just want to decide whether you want to see the movie. Okay? So the question then is, the significance weighting, you should sort of be dependent on the shared experience, the total number of items that you are co-rating. You don't have to rate them exactly the same, it's just you co-rate it. And if it is less than some small number, then, so basically what I can do is, I might say, in this case I'm saying, the significance factor increases linearly from 0 up to 50. And then after 50, it just becomes equal to 1. So you've seen 50 movies with somebody, then presumably I think you have just enough, as much experience, common experience with them as anybody else. So they should not, they should not be penalized for not having enough common experience with them. Okay? So that's your significance factor, you multiply that. That sort of takes into account this problem. One of the problems that not every user has equal amount of common experience with every other user. Here, when I said common experience, I'm obviously stretching the word. It's like you both separately experience the same book in your own rooms. I'm not necessarily putting you in the same room and experiencing it together. Okay? But still, you co-rated that. That's the question. Okay? So that's a useful addition to do, and that improves the collaborative filtering when it's user-centered. You can get rid of all these complications if you are doing item-centered collaborative filtering. Because in that case, you just compute the correlation clusters for the items, the way you computed correlation clusters for the words in the midterm, right? And then for each word item, you can then say, what are the k closest items for this? And then I can just start suggesting those to you. Okay? So that one slight advantage of this over correlated, over user-centered prediction is you can at least say that these items are just functional synonyms. They seem to co-occur together. And so that's why I'm recommending it to you. So you can explain your recommendation a little bit better than the previous case where you just say, there is this intermediate called users that I don't want to tell you about, but those users seem to be having the same habits as you are, and they have this item, so you should also have it. Okay? So collaborative filtering, by the way, is a forced way, the way Amazon forces people to keep up with Joneses. You keep up with your neighbors, where neighbors are computed in the similarity. Okay, yes?
So I can sort of collab, collaborative filter looks more like the other kind of stuff that is not.
What kind of stuff means? The content-based, you mean?
Yeah.
No, because in both cases, I'll remember that. So the interesting thing is, the item-centered collaborative filtering, each item was a vector in the space of users. The features, the user feature doesn't have any meaning. So if in fact, I can't tell you, so if I were to recommend to you this book using content-based filtering, and you say, why did you recommend it to me? Then I will say, well, the words, economics and computer science seem to occur very much in the books you buy. And this book has economics of computer science in its title, so that's why I'm recommending it to you.
But you can use these as a judge for those if they are the same kind.
I don't know. They're what?
Suppose that these are books also, like those, same domain. You can use these as judges for the decisions you take there.
I still don't understand what to say.
Yeah.
We should talk though. I mean, so basically in this case, you're still not doing anything domain specific. The items can well be that if you like this book, you would also like aspirin. Okay, where aspirin is not a book, it's just bought. People who bought this book also bought aspirin. So I will put it together. Okay, it's just an association. It's not, there is no content-based understanding of the items. Okay? So that's the collaborative first filtering from the item-based direction. And then I asked you to look at the Netflix prize paper. We talked about it last time. And one cute thing there is that actually the winning system, mostly depended on. So in terms of the use of content-based and collaborative filtering, I think that paper, if you read that, you would know that Pandora, which is this music service, actually does content-based filtering. Okay, and to be able to do content-based filtering, they had humans who listened to different songs, and they have come up with a set of features for describing songs. Okay, hard tempo, fast tempo, metallic, this, that, etc. And then for each song, they make it a vector in the space of these features. And then they suggest new features, because of that, since they only deal with songs, and they don't basically sell you anything else, they just talk to you about, they deal with songs, and they can essentially care about, if you actually say, in fact, the usual thing that Pandora, I don't know how many of you use Pandora service, you can pick a song and say, I want to make a station around this song. And so it just essentially computes all the songs of, all the vectors that are close to this vector, and then just randomly starts playing those two. So Pandora uses content-based filtering, and somebody is paid to come up with features, and a whole bunch of undergrad students have been paid to, write the vector representation for each of the songs. Okay. Whereas for Netflix, you could have done that too, but actually the thing that was working better for Netflix turned out to be collaborative filtering. It's not obvious. I could have said that is the case, but it seems to have worked better for Netflix. Okay, and so in fact, the point that this particular paper was making is it was doing collaborative filtering, but first before doing collaborative filtering, they actually did LSI on the item user matrix. Okay, so that you come up with a factor space where users as well as items are dots, are points in this factor space. And remember the picture that we had where some things on statistics, some things on databases, and then when you did the factor space, then all the statistics ones kind of are closer to each other, all the database ones are closer to each other in a different direction. Okay, that's the kind of patterns you're hoping to find by doing LSI. And this picture they're basically saying, so they first factorize the matrix, and then this one is just a two factors. So they did reduce the dimensionality to 2 dimensions, where the dimensions are just some arbitrary linear combinations of the original dimensions. Okay, and then in that, if you now both the users and the movies would be vectors in this space. So I'm only showing movies because you don't know users. I mean, what if I tell you the user N7 lives here, user N9 lives here? You don't know who these people are. If it's you and your friend, then you might want to know where you are. But in particular, for the movies themselves, this is sort of a nice, interesting pattern that develops. Okay, and so you take this particular representation and then do your collaborative filtering. So you start with reduced dimensionality and then do everything I said before, either item-centered or user-centered collaborative filtering, and that works well. And one technical point that they make, which I would not be able to go into too much detail here, is again to do LSI or to do basically any of these techniques on collaborative filtering. Your problem is that there may be too many null values for the ratings. Most items probably haven't been rated by most people, which actually then means that when you take 2 random pair of users, then the common items that they're rated is likely to be even smaller, right? And so there is this problem that you are doing decisions based on small amounts of information. Okay, so how do they deal with this? There are 2 ways of dealing with this to make the LSI look better. So first of all, in the case of LSI, actually, it does matter that, remember LSI is all about distances between points, right? And if in fact one point, each user, let's say, there are like 10,000 movies, each user, there are 10,000 movies, each movie is a vector in the space of 1 million users. Okay. Now, if I'm computing the distance between two items, and if I'm ignoring all the dimensions that are not common between both of these, then I'm essentially computing distance between their projections rather than themselves. Do you understand what I'm saying? So if the true points are like this, let's say the true points are like this, but one of these guys, in 3 dimensions, one of these guys didn't actually rate one of the dimensions. So then you will actually wind up getting projection right there. Both points would be right next to each other in the projection. And that distance is not the true distance in the actual high dimensional space. Do you see what I'm saying? Okay? And so it's actually a big issue in doing the LSI that these, some of the dimensions are not being considered originally. And so you need to get some numbers there. So either you have to somehow consider distances only on the dimensions which have common ratings, or impute or just predict what would have been the missing rating. And so the prediction part is actually what I'll be talking about next, but the way they could have done it essentially is for each user learn a content-based filter. And use the content-based filter to fill up the missing ratings for the rest of the movies that they haven't yet seen. And so you have now a pseudo vector which is full. Some of them are true ratings, some of them are predicted ratings based on content-based rating. Then you do LSI. That's one idea. The other idea that they actually went with is they only compute the distance in terms of the reduced number of dimensions. But then if they do that, they are likely to wind up doing overfitting. So for example, they might wind up saying something like, a particular feature is completely indicative of whether or not you will like this movie. And the feature could be U1700. That means the user 1700 liked that movie because of which you will like the movie. Okay, that's overfitting. Okay, and to avoid that, they essentially basically regularize the learning and they say none of the weights can be larger than a certain value. And that's sort of advanced. We can't actually go into this. It's a different way of doing SVD where you are allowing computation of distances over only the dimensions that they share. Okay, but then you are also penalizing high weights for any particular dimension. And that's actually what they wound up using in the paper. But the bigger challenge is both of these approaches are basically dealing with the same challenge, which is there are too many items that are not rated yet. Too many items that are not rated yet. Okay? And so you want to predict, in this case, either predict or live with the fact that they are not rated. Now, in terms of predicting, so actually I'm going to look at a more complete example of just predicting and then combining it with collaborative filtering here. So anyway, these are the problems with collaborative filtering. We talked about this cold start. There needs to be enough other users already in the system to find a match. If you're the first user in the system, they can't do collaborative filtering. Sparsity. If there are too many items to be recommended, most vectors are sparse. So most items are not rated. That means most pairs of users are very few commonly rated items. Okay. First rater cannot recommend an item that has not yet been previously rated, even if there are lots and lots of people in there. Popularity bias cannot recommend items to somebody with very unique tastes because they don't have enough common ratings with anybody that works well for them. So if your k nearest neighbors, remember what collaborative filtering is doing, it's trying to find k nearest soulmates. Okay, these are the closest soulmates. What if the first soulmate to you has similarity 0.0000001? I will still use them because you asked me to just use k users. I'll just use the k users. But my prediction for you is not going to be particularly good because I'm getting you pretty lousy soulmates. Okay, and so that's the problem. And so if you have non-popular taste, you are not likely to get much of a good recommendations. Okay, so that's basically some of the problems of collaborative filtering. If you look at it from that side, content-based filtering has lots of advantages because it doesn't require data on other users. It requires but it only recommends to the users. I mean, it can also recommend to the users with uniqueness, and it can recommend new and unpopular items, and it can provide explanations for the items, saying the reason I'm giving this to you is because you like these words or these features before. Okay, and of course, the entire field of text categorization, classification learning is at your fingertips that you can use for content-based filtering. But the problem with content-based approach is, as I said, it's domain specific. So you cannot suggest aspirin based on books. Okay, so somebody has to sit down and write things in some feature form. Okay, now interestingly, for text documents, you think the words are the lowest level features. Okay, at least that is there for you. For music, that is not even obvious. In fact, for the music, in fact, the lowest level features would be Fourier transform coefficients, or something like that. Okay, and it's very low level. Just as for text, words are extremely low level features. In fact, it's much better if you talk about features such as the westerns, the non-fiction books, or the historic romances, things like that. None of these are words. They are actually high-level features about books. If you classify your books in terms of those features, you can learn much better predictors. Okay. So again, in general, just as Pandora had to come up with reasonable features for the music that they're trying to that they're trying to recommend to you, anybody who's doing content-based filtering has to come up with reasonable features for that particular domain. Okay. And of course, it cannot exploit the wisdom of crowds because basically you have no connection to the rest of the users. You're only looking at your own world. Okay. So now, how about combining both of them? As I mentioned, you can use content-based filtering to fill up the missing values of the collaborative filtering approach. Okay. And the interesting thing is, if everybody has 100% of the items rated, then every pair of users have 100% of the items co-rated. That's by definition, right? Okay, so what I'll do is I will start with a user ratings vector, a particular user's rating vectors, and the dark green, whatever that thing, those are the items they have already rated, the others they haven't yet rated. Now based on the ones they have rated, I will learn a content-based predictor. Okay, maybe naive-Bayes classifier. And then using that naive-Bayes classifier, I'll go ahead and rate the ones that haven't yet been rated. So these are, if you remain true to your original preferences, you would have liked these at this level. Obviously, they're not certain true ratings, but they are predicted ratings. So now I have a user vector which is actually full. And then basically the co-rating problem would be gone now. And cold start problem also will be gone. Most of the problems I talked about would be gone with respect to this. Except these ratings are bogus ratings to some extent. So the question is, if I start with this, will I do better in terms of accuracy of recommendation than collaborative filtering without this? Okay? And the answer is actually yes, you do better. Okay? So predicted ratings, as long as those ratings are predicted based on your past history, okay, are better than just ignoring what you might be saying. Okay, so this works basically, so combining content-based and collaborative filtering this way works better than either. That's kind of nice. Yes?
You're predicting what if the two movies don't have anything in common? How do you predict?
What do you mean? No, presumably to learn, first of all, remember that this content-based, this is a pretty costly thing to do though. You are learning a content-based filter to use for each user first. Okay? And if you were able to learn a content-based filter, it will give you some probability. So your question of what if these two movies have nothing in common is like asking in the old restaurant scenario, what if this new restaurant that this guy is going to has nothing in common to any of the restaurants he has gone to? As long as there is a reasonable set of training examples, you will be able to have some things common some features common, and you will be able to use that in the naive-Bayes classifier to compute the probability that you would like versus probability that you won't like. And you'll pick the one, the probability that you like is higher, then you'll assume that your rating is higher. Okay? So that's basically the content-boosted collaborative filtering. And this was actually an idea that these guys say in that paper. These guys say in this paper that they tried it, but it didn't work as well as this other idea. Okay, so I'm just saying this. But for a textbook, for an introductory course level, it's useful to know that this is a useful idea that you can use. Okay, now the last thing I want to say here before moving on to advertisements is there is a certain level of circularity here. I didn't have content-based. Why am I not directly using content-based filter? I'm actually using, so in fact, the interesting question that you have here is when you do this, then every user has predicted rating to every item. Then why do collaborative filtering? Presumably somehow the ratings that you predict using collaborative filtering are better than the rating that you would have predicted to this item based on your content-based filter. This is a mind-numbing thing. So the idea is there are 100 items. Okay, I'm trying to figure out whether or not I would like item number 57. I can learn a content-based filtering based on the items I liked, and I come up with a rating for 57, which is, let's say, 6. That's my best guess. Now, by doing this, what I'm doing is not only am I doing this to myself, I'm also doing, everybody is doing this content-based filtering and filling up their vectors. And then I'm using them to re-predict what I should be liking, how much I would be liking this particular item. 57, which by content-based filtering I liked about 6, might be predicted as I would like it about 4.5. And what the results, empirical results are saying is that that would actually be better because content-based filtering has its own problems, just as there may be not enough features in common and you're jumping to conclusions. Okay, so there is some sort of circularity as if you bootstrapped yourself, content-based was used to bootstrap the collaborative filtering. So the last thing is why not do this, without even having collaborative filtering. So go back to text classification, just simple text classification. And we talked about the fact that, most of the problem is that in learning is the number of labeled samples. Okay, suppose I'm doing spam versus non-spam, and I'm basically, for like these many documents have already been pre-labeled as spam versus non-spam. Okay, obviously, if a learning algorithm that does well with fewer examples is better than the one that does well but many more examples, because the other one requires a lot more training data. Okay, so my question in this case is, suppose apart from these many, so if I'm here, I have 50 training examples. Okay, and this guy is actually just using those 50 training examples, and its performance on the test data is whatever the percentage. My question is, suppose I also give you, and for both of them, I give them another 10,000 unlabeled documents. This is basically, in the math example, these are the 50 worked out problems and 10,000 problems which haven't been worked out, but they're there. The question is, could you use the problems that haven't been solved to improve your performance? And the answer in this case, as you can see, is that in fact it is possible. This is a learner which uses the unlabeled examples, and with 50 training examples, 50 solved examples, it still was able to reach a much higher accuracy. Notice that as the number of solved examples keeps increasing, clearly they will both sort of reach the same level. Okay, but this is beautiful, right? I mean, this is sort of exactly how human learning works. That's why you not only have answers to the odd problems in the textbook, but you also have even problems. Why not just have odd problems? Because those are the ones with the answers. The even problems, you try them out, and you don't know whether the answer is correct or not. And yet, the very act of doing them, you learn something. right? Okay. So can classification learners do that? And here is a technique that I'll tell you how to do it. It's very simple. So I have, let's say, originally, let's say, 500 or 50 examples. I learned, and I always have a whole mass of unlabeled examples sitting. Okay, so 10,000 unlabeled examples sitting. Okay, so I learned a naive-based classifier on the set of trained examples, labeled examples. On the set of labeled examples. I got it now. Now, I apply that to the other unlabeled examples. Then I will know their class information, if my learning was correct. I'll go ahead and assume my learning is correct. So now I have answers to 10,000 plus 50 examples. I relearned the naive-based classifier on these 10,000 plus 50 examples. And then keep doing this until my performance on the training data is not changing, on the test data is not changing. Okay? If I do that, that's exactly what you're doing in your math book. I mean, you do a few problems for which the answers are given, and then you start doing a few problems for which answers are not given, and as basically you're doing the ones for which answers are not given based on what you learned from the ones for which answers are given. Okay, so that's exactly what you're doing here. It turns out this idea actually works in practice. The only difference, the one thing that you have to do is remember that when you compute the naive-based classifier, so suppose you have a C and not C. Let's say suppose there's just two classes, C and not C. Okay, and you are computing probability that a training example belongs to C and probability that the training example doesn't belong to C. And then you're just basically assuming this, if this is bigger than this, you will say example E corresponds to class C. That's how you are going to label the unlabeled example. However, suppose this is 0.51 and this is 0.49. You're not really that sure of your labeling. The ones that people gave, they know for sure what their labels are. The one that you are guessing, you're not for sure that the labels are, definitely class C. So instead, what I would like to say is this example is 0.51 of class C and 0.49 of class minus C, class negative C. So remember, in the whole naive-based classification, you are counting the number of examples in a class. Previously, an example would either be in the class or not in the class. So it has 1 and 0 as the weights. Now, an example can be 0.51 in this class and 0.49 in this class. So it gives a weight of 0.51 to one class, 0.49 to another class. So you keep track of the posterior distribution of the naive-based classifier and use that to figure out the fractional membership of each item, each unlabeled example in different classes. And so then the next level, you essentially use these fractional membership numbers to compute the new naive-based classifier. And keep doing this until your performance doesn't change. And this is the first idea that you got in this class, essentially, of the idea of semi-supervised learning. Where here you have supervised learning is the part where you have examples which have labels. And the examples which don't have labels are not supposed to help you. I mean, that's not trained, that's not labeled examples. Web is full of mails. Okay, only some of them are known to be spam versus non-spam. Many of them are just mails. You don't know whether they're spam or non-spam. So I can always give you unlabeled examples, and if you have the ability to improve your performance by using the unlabeled examples, you can be better than somebody who can't. Okay? Now the interesting question that you want to think about is exactly why does this work from an intuitive sense. I mean, in fact, there is a theoretical way of explaining this, which is essentially, this turns out to be an idea called expectation maximization algorithm. If you do an AI course and an ML course, you will learn about this. Okay, but the more interesting question for us is, can we actually give an intuitive explanation as to why unlabeled examples help? And to understand that, suppose I have made up in the math book, right? There are 5 problems which have answers, and then I gave you 10,000 problems. I just made them up. They're just random strings of words. And you don't even, when you read this problem, you don't know whether it has an answer or not. Is it a well-formed problem, etc. Giving those kinds of gobbledygook is not going to help you improve your performance. Do you see what I'm saying? In fact, the hardest part is coming up with the problem, not solving it for you. Okay, if I can come up with a problem, then I can also solve it. If you define coming up with a problem as coming up with a problem which has an answer, then I can also solve it. If you say, Rao, come up with some problems, whether or not there are answers, I can write a large number of them. And I can give you all of those, and you will waste your time and won't learn anything. Okay, so even though you think unlabeled examples are useless, they're still examples. They do have the same structure as good math problems. That's why you are able to do this and bootstrap yourself. You're not getting something out of nothing. You're getting something out of partial information. Somebody spent a lot of time making these examples. Okay, in the case of mails, these are real mails that people got sent. They're just unlabeled. If you are, since I'm telling you, I can use unlabeled mails, you might be saying, okay, here are true mails that some user said spam versus non-spam. Here are 80,000 randomly generated documents, where I just randomly generated them. Pick, words randomly from the vocabulary, made a document. And that's a bag of words. Can you improve your performance that way? No. Because they're not mails. They were not generated by anybody who actually was sending mails. Okay? So that's the thing you tend to miss when you think in terms of unlabeled examples. Unlabeled examples don't always have to help. They will help exactly when they were taken from the same distribution as the labeled examples. Okay? So that's a pretty, deep point actually, as far as some of the topics in this course are concerned. This is like complete above some of the other things we're talking about. Okay? So I hope you understand that. So I'll start talking about recommendation systems now and go for the next 15 minutes and probably part of the next class to computational advertising. Okay. So we are still in recommendation systems, except we are thinking of advertisements, where Google is recommending that you click on this link whenever you are searching for something, right? Except when Amazon recommends that you might be interested in this book, presumably they are only trying to improve their own bottom line. When Google, by selling that book to you, when Google is recommending this, it's like they're acting as a publisher of advertisements. New York Times is not selling everything that it's advertising. Although more recently, actually, New York Times is not getting enough advertisements, so half the time they just advertise themselves in the paper saying, we are such a great paper, please buy us. And so if I haven't bought it, I won't know that. But anyway, so normally they're supposed to make money by advertising Macy's and all these other people. Do you understand what I'm saying, right? So the question, so we'll talk, and you know that advertisements are like a huge deal. Everybody on the internet makes money based on advertisements, right? So we want to understand some things about it. Once again, just as everything else, you can do an entire course on this, okay? And I'll just do it in one class, hopefully. 15 minutes now and something next week, okay? So here's the history of web advertising. In the beginning, they were just doing banner advertisements, which is sort of like, print advertisements, where you just put it there, and if you like it or not like it, they will put it there. Even if you are not in the mood for buying clothes, the next page is Macy's advertisement. So, you have it there. And if not enough people are interested in buying clothes, there is no point in doing a Macy's advertisements. And if, for example, the economy is in the dumps, there is no point in making full-page advertisements for Rolex watches, because there are not enough people likely to buy it. Right? But that's the only thing you know. You don't know much about the user, and so you cannot actually direct the advertisements to the context that the user is looking at. Okay? So in the beginning, that's what they were doing. This is how print advertisement works most of the time. And, that's what, the web advertisement also tried to do. In fact, they also had even totally dumber ideas than this. I told you that InfoSeek, the search engine, would show the 10 results, and say, if you pay us $10, we'll show you the next 10,000 results. Okay, so I'm not making this up. This was the idea they had of making money by doing, by selling stuff. But anyway, in this case, the display advertisement was there before, and the other idea that came about, well, apparently in 2000, but it looks as if it's been much longer, in my view, is there used to be the search engine which would essentially say, who the heck cares about, users? Why should we do nice things to users? We will just sell the first page positions directly to the advertisers. So if you say White House, and Herman Cain really likes White House, so he'll pay $1 million. So he will put, the overture would put Herman Cain #1 as the White House result. Okay, #2 would be whoever else who pays the next. And this would be the search result. So there would just be one window. First Herman Cain, then somebody else, and somebody else, and somewhere below, maybe in the 15th page, is Obama with his real White House. But he didn't pay enough, and so he didn't show up in the results. Okay, so that's what Overture was doing, and it was actually working fine to the extent, apparently there are people, I don't know who these people are, but apparently there are people who go to web and search for shoes. They'll say shoes as the keyword. I mean, obviously I'm not one of them, so I don't know how these people work, but so if you're doing things like that, shoes, then, there are tons and tons of people selling shoes. And Overture would say, you want to go first, Nike, you want to go first as the shoes guy, you pay us like, $10 million, we'll put you first. That's what they were doing, okay? And the one big difference with respect to the print ad was, in the case of print ad, once Macy's pays the money, and also television ad, okay? Once Macy's pays the money to New York Times and makes this full page ad, even if none of us looked at that ad, they already paid New York Times the money. Do you see what I'm saying? They don't basically have any sure way of making sure that people are forced to look at it. So in fact, they had to come up with all sorts of interesting ideas. How do you make people look at things? How many of you still read magazines? And if you open a magazine, sometimes things fall through it, and then you have to bend and pick it up. The guy who invented that became a billionaire. You see what I'm saying? It's like, just basically make people pick it up and then you have to see for a 3-second period, 3 millisecond period. That's a great idea because, most of the time we are not looking at the ads. And so you just have to make sure that somehow, things will happen. Sometimes Macy's will put some scent there. And if you like the smell of that scent, you might